So we've worked out a nice algebra of sets on this set, which we called this, and a nice additive, in fact, countably additive function on this. So countably additive, that means it qualifies as a measure, right? So we actually have a measure. Now, the reason we're focusing on the unit interval, like really we should care about r, right? Not just the unit interval. But if we want to bring in r into the picture, then we might actually want to allow for lambda to take the value infinity sometimes, right? Like what should lambda of r itself be? It should be infinity, whatever that means. Well, what it means is a point in the extended real number line. But I kind of just don't want to introduce the extended real number line. It's really, I feel like it's just not going to add much to what we're doing yet. If I change my mind later, I might introduce it. But for now, I'm sort of relying on the unit interval as a bounded stand-in for r. Things are just as interesting in the unit interval, which could stand for any bounded interval, as they are in r, so far at least. Okay, so let's go to Rn, and by Rn I mean our nice bounded version of it that allows us to keep going without introducing the extended real numbers. So here's what I really mean by Rn. I mean unit interval n. So that just means the unit interval Cartesian producted with itself n times. So the collection of n tuples whose coordinates are all in the unit interval. So this is a set, and we could try to define, let's see, so I want to kind of get the same stuff that we achieved here, but for that situation. So here we started with a semi-algebra of sets, and then we built up to an algebra. We started with a version of lambda that only worked on the semi-algebra and was additive, and then we used our theorem to extend it uniquely additively to the algebra of sets. And then we used our criterion from the previous video, the compact class criterion, or whatever you want to call it, to get that this is countably additive. Can we do all that same stuff, but in n dimensions? So where to start? How about the semi-algebra? What should our semi-algebra of sets be? So here's something we can do. How about we take the things from our original semi-algebra and just take n-fold Cartesian products of those. So like this. Running over all these in our original semi-algebra, this one. Our semi-algebra on the unit interval. So in other words, look at all the n-fold Cartesian products of intervals. This is the collection of intervals. And let's just temporarily call this S for now. Is that a semi-algebra of sets on this thing? Well, it turns out yes, it is. So here's my coded kind of way of quickly describing what needs to be checked. Is the empty set in there? Yeah, the empty set is, this thing contains the empty set. The empty set is technically an interval. And so the empty set is one of these products. So that's fine. Closed under intersection. This one is actually not so hard to check. Are complements finite disjoint unions? So this upside down pi symbol is often used for unions of disjoint sets. It's called disjoint union. Are complements finite disjoint unions? So let's see. Let's think about the n equals 2 case just for a moment and look at a picture of what's being asked here. So let's say I take, how to start this? Let's say I take one of these things and then think about its complement inside the unit square, I guess is what I'm looking at. So here's the unit square, 0, 1 squared, the unit square. And then let me take one of these guys, let's put it in green, it could look like maybe this, including one edge and not including another edge, whatever. So it's going to be a product of intervals. So some rectangle inside the square. Then what happens when I take the complement? Do I get another product of intervals? Definitely not, right? Product of intervals basically is going to look like a rectangle that contains some of its edges and doesn't contain some other ones. If I just delete this from here so that I get the other stuff, if I take the complement and just have a hole here, what I have is definitely no longer a rectangle. But that's not what I need for semi-algebra. What I need is that when I take the complement, I get a disjoint union of finitely many things in the semi-algebra. And is it that? Yes. Slice up the complement like this. Slice it up like this, and then look at these rectangles here. It's a union of these rectangles, right? So the answer does turn out to be yes here, but can we do a little bit better than this picture? It'd be nice to do better, since this is kind of important. This is our treatment of Rn, right? I feel like it deserves a little bit more respect than this little picture. Okay, so I promise I'll come back to that. But let's just think about, let's say we accept for now that this is a semi-algebra of sets on here. That's nice if we have that, because then there will be automatically unions of products of intervals, so like unions of rectangles or unions of cubes or whatever, will be, maybe I shouldn't call it this, will be an algebra of sets. That's automatic, right? It's automatic by lemma 1214. So lemma 1214 tells us that if you have a semi-algebra of sets, take finite unions of things in there, and then you get an algebra of sets, specifically the one that's generated by that semi-algebra. So that's nice. If we show this is a semi-algebra, we get our nice algebra of sets. And then if we have an additive function, lambda or mu or whatever, let's just call this one mu. If we manage to get an additive function on S, then it will automatically have a unique additive extension to A, thanks to a different result that we proved. So we only need to define mu on S. Now how might you define the measure, the area, volume, whatever, the measure of a set? How might you define specifically the measure of a rectangle or cube? That's all you actually need to answer in order to get measure for finite unions of those kinds of things. Okay, so hopefully what you're thinking is, if I take a product of intervals, then make the measure the product of the lengths of all those intervals, right? In the sense of lambda, the same lambda we were talking about previously, the one that takes supremum minus infimum of these intervals. So define it like this, where this is actual multiplication of numbers over here. Now, is that additive? If we can show that this is additive, then it'll have an additive extension to the algebra of sets generated by this. That would be nice. And then maybe we can show that that's countably additive by using our wonderful criterion here, where we try to find a compact approximating class. So question, if you try to define it this way, then is it additive? Now, additivity in the, when we were thinking up here about with lambda, so the like sort of n equals 1 case, additivity of lambda on the semi-algebra of intervals was really about things like this, right? And yeah, it's a little bit annoying to make sure that it always ends up in this situation, but it comes down to just a telescoping sum, and you can handle it. It's not so bad. But here a lot more can happen. So additivity will care about those situations where a product of intervals, where you have a family of products of intervals, so a bunch of rectangles, in the, say n equals 2. Then it's rectangles inside the square, right? And sometimes you'll take a bunch of rectangles, disjoint ones, and their union will be another rectangle. And it's those situations that additivity will care about. So, like, not what I drew here, but things like this, for example. Like, here are 4 rectangles whose union is a rectangle. And they're disjoint. Well, you can make them disjoint if you include and exclude edges in the appropriate way, right? So, like, maybe include the boundary here, and then don't include this one here, but include this one. You get what I mean. So countable additivity will care about these situations. But when you try to work this out, it does not break down across the product in such a nice way. And let me show you an example that demonstrates sort of what I mean. So you could have this, for example. Something like this. So say these 5 rectangles here, the product they are all in the semi-algebra, so they're all like products of intervals, and if you include and exclude edges in the appropriate way for those intervals, then they can be made to be disjoint, and they can be made to hook up properly so that their union altogether is this big rectangle. So this is exactly the kind of situation where you would have something to check when you want to know whether mu is additive on the semi-algebra. Okay, actually, yeah, trying to draw things live never works as well as I want. This is not the example I wanted, because this one splits nicely and allows you to try to use maybe some kind of induction when you're working this out. If you cut it here, then it's one part of it is a union of fewer rectangles. The point I'm trying to make is that some cases don't split so nicely. Okay, this is what I meant. So say these like 5 rectangles here, and it's the same idea. But I just want you to see that, like, when you're trying to prove that mu is additive, this is like one of the cases you have to think about. So how do you come up with a general proof that mu will be additive? And this is even just n equals 2. You can imagine how complicated things might get for larger n. So I don't think this is... I'm not trying to challenge the plausibility of mu being additive. I hope you feel that it's plausible. I'm trying to challenge sort of how trivial you might think the proof is. I think it does actually take a lot of effort to work out the details. And thinking about this a lot is the reason this lecture was delayed in being released. I kept thinking it would be really easy, and there's just a lot of things to get in order. Okay, so far I haven't really said very much here. I'm just leaving a bunch of open questions, but I'm doing this to justify the effort that will go into filling in details. So some questions. We can do this. Is this a semi-algebra? We can try to define mu like this. Is it an additive function? If all that stuff works out, we can go to the algebra of sets generated by S and automatically extend mu to an additive function on that algebra of sets. When we do that, does it end up being countably additive? Can we find a compact approximating class for mu in that situation? So this is really important, I think, to get right and to get the details down, because this is actually the Lebesgue measure. So once we work this out, mu will be our Lebesgue measure. This will be on our stand-in for Rn, our sort of bounded version of Rn. And hopefully we'll get to extend it beyond just an algebra of sets But this is our first step, is to trying to get to the algebra of sets and get to countable additivity on that. All right, so I think I think this lecture is okay. So all the stuff that I talked about so far is what I had written down for what to do in the first 10 minutes of today's lecture. I don't know if I'm just sleepy or what, but for some reason it's dragged out. So I think I will do most of the detail work actually on Friday, and then hopefully either end of Friday or Monday we can get started with the next section and start thinking about sigma algebras again. So I might just do a little bit more here. I don't know how long this video has run, so let me see how much time I've got left.